Thank you very much. It is such a pleasure to be here in Belgrade, to be at the New Technologies in Education conference and exhibition. It really is. I'm Miles Berry. I work at the University of Roehampton, training the next generation of outstanding teachers. Alongside that, I've been part and parcel of the process of designing and implementing England's computing curriculum. And we're 2.5 or so years into that now. I think we're starting to learn some lessons about what makes for effective practice when it comes to computing education. And that's what I want to talk to you about this morning. It's fair to say that our computing curriculum is a broad and I hope balanced one that draws together ideas of the foundations of computing, the computer science, the theory, as well as programming, coding, algorithms, and the like, applications, being able to get useful things done with a range of different technologies, as well as the implications of this for me as an individual and for us as a society. And any computing education ought to include all three of these elements. Much of what I'm going to say this morning focuses just on that foundations tier, the theoretical computer science, the programming, so forgive me if I don't pay enough time and respect to the other two branches of our computing curriculum. So how is it going? Well, before we implemented it, and once it had been designed, teachers were really very worried about this subject. When we did the survey, we found only 33% of teachers felt confident or quite confident in terms of teaching this new subject, computing, mainly because they never learnt this when they were at school themselves. Now, 2.5 years in, Ipsos Mori did a survey for British Telecom, our leading telecoms company, and the results there is 81% of British teachers now feeling quite confident or very confident in terms of teaching computing. So I see this as a tremendous success. The children themselves are loving it. Only half a year in, by 2015, we already had 24% of children said that computing was now their favorite subject on the curriculum. And that is great, it really is. And I hope that figure continues. We have rapidly increasing numbers of our young people who are choosing to take a formal qualification in computer science at the age of 16. There's been a massive increase in that over the last 3 years. And we're starting to see a slight upward trend in the children, young people, students who are choosing to take a formal written qualification in computer science at 18 plus as part of their school leaving qualification in terms of preparation for university. When it comes to university entrance, we're already seeing an upward trend, reversing the previous downward trend. We're seeing more and more students choosing to study computer science as their degree subject, and I'm one of the ones who are optimistic here. I think that trend is set to continue as more young people come through school being excited about programming, being excited about the ideas of computer science. So the whole thing in one slide. What are we learning about teaching computing in English schools? Well, broadly speaking, these 10 things. I'm going to go through these in a little bit more detail in the slides that are to come. This is based really on just anecdote of me going out into schools and talking to teachers, of me listening to what teachers are saying in the Computing at School discussion forums and our Facebook groups, and so on. I'm backing this up with some of the academic research in this field, but there is no sense in which this is rigorous, randomized control trial studies proving that all of these 10 things work. This is very much a presentation of teachers' practice. Other people have done more of that sort of serious academic study of this, and I would refer you to Shuchi Grover's work at Stanford Research Institute. She has her baker's dozen of 13 things around teaching programming, classroom strategies for this, and there's a lot of overlap between her list and my list. My friends Sue Sentence and Andrew Chismadia have done the survey. They've asked 339 English computing teachers, what are you doing in your classroom? So they've got a lot more evidence to support these statements than I can offer you. And again, their list very, very similar to my slightly less formally derived list of what we're learning. So on with the first of these. It's very, very easy to focus on the programming, to focus on the coding, but it isn't actually about the coding. We want our young people, our children, not merely being able to type in lines of code. How exciting is that? We want them being able to think about what they're trying to do here. And we have, as a foundation for that, Seymour Pappert's work back in the 1980s. He saw how children who'd learnt to program could use concrete computer models to think about thinking, to learn about learning, and enhance their power as psychologists and epistemologists. This isn't about coding as an end in itself. Yes, some of our young people will get jobs in the software industry. That's great. They won't all go and be software engineers when they grow up, heaven forbid. But through learning to program, they learn to think differently. They look at problems, they look at systems in different ways. There's a metacognitive element to this. They learn about learning, as Pappert says, they think about thinking. So the initial sentence of our new curriculum starts with this level of ambition. A high-quality computing education equips pupils to use computational thinking and creativity to understand and change the world. And surely, this is what education should do. It should equip young people to go out there and understand the world in which they find themselves, an increasingly technologically dominated world, and to be empowered to make a positive difference to that world. I think the computational thinking is that about understanding the world, about looking at systems in a different way. We have Jeanette Wing's work on computational thinking, which sets the foundation of this. Computational thinking, the thought process involved in formulating problems and their solutions so that the solution can be presented in a form that can be effectively carried out by an information processing agent or computer, as we might call it. It's the first stage of any computer programming. Think about the problem, understand the system, then and only then go off and write some code. Yes, the coding matters, but so does the thinking about it. Roy P., writing back as far back as 1983, saw that young children, elementary school kids, could learn to code in Logo. But they wouldn't get the subtleties of that unless a teacher came in and showed them how to take their programming beyond the draw a triangle, draw a hexagon type programs. Nor would they actually think about things correctly in a computational sort of way, what he called planning skills back then, unless a teacher intervened and taught those computational thinking, those planning skills, alongside the much more visceral coding experience. My second point is that you don't actually have to use a computer in order to understand many of these ideas of computer science. When we're working with young children, we take many of our metaphors from the world of food and drink. Think, if you will, of your recipe for making pizza. That could be just phone the pizza company and get it delivered. That's the sort of managerial approach, get somebody else to solve this problem. Or it could go to a lot of detail about making the dough and kneading the dough and creating your own tomato sauce to spread on that. We have layers of abstraction there. But the recipe for pizza is essentially an algorithm to solve a problem. You can teach so much of this algorithmic thinking, abstraction, decomposition, without going anywhere near an actual physical computer. We can bring that algorithmic thinking to common sorts of questions, puzzles, problems that we might do in a maths lesson. So, good maths lesson, I'm thinking of a number. Ask me yes or no questions to work out what my number is. And if you work with sufficiently young children, they come up with a really bad algorithm for this. They do things like, is it 2? Is it 5? Is it 103? And that is slow. Believe me, it's slow. It is also really difficult to keep track of the questions that have already been asked. With a little bit older class, they might take a much more systematic, computational approach. Is it 0? Is it 1? Is it 2? Is it 3? It's no faster, but it means we don't have to listen to what everybody else in the class said, and we're definitely going to get there with an algorithm like this. This is algorithmic thinking. This is a systematic way of solving this particular, in this case, relatively easy problem. Later on, we will refer to this as linear search, and it's an important search technique, but it is painfully slow. Further up the school, children for themselves will come up with a much better algorithm. Is it 64 or more? Is it 32 or more? Is it 48 or more? This sort of divide and conquer, zooming in on the number itself, so much more efficient. Pick a number between 0 and 1,023, and I will get there in just 10 questions. Between 0 and 1,000,000, and it will only take me 20 questions to zoom in on that number. A much better algorithm for solving the same problem. This doesn't need a computer in order to do this. In English schools, we still teach children how to use dictionaries, not merely to type in the word into Google and see the definition there. When we teach children to use a dictionary, we don't say, well, just open it at random and keep doing that until you find the word you want. We don't say to them, well, start at the first word, then look at the next, then look at the next, then look at the next until you get the word we want. We teach them to open it halfway through and look in which half it is, and then look in which quarter it is, look in which eighth it is, to zoom in, to narrow in on the word. Why do we do that? Because that's the way to use a dictionary. We think that it is much easier to read code than to write code. Yes, we want children making things, more of which later, but we also want children being able to think about code. And this does seem, from what we know about undergraduate computer science education, to be a very effective way of teaching children to program. So we have that built into the English national curriculum. At Key Stage 1, our 5 to 7-year-olds, children should be taught to use logical reasoning to predict the behavior of simple programs. 7 to 11-year-olds, children should use logical reasoning to explain how some simple algorithms work and to detect and correct errors in algorithms and programs. Yes, running the code and finding it doesn't work, that's fine, that's an important part of the experience of learning to program. But far, far better to read the program and then say what won't work when it is run. That's a higher order thinking skill, and this continues on to our 11 to 14 curriculum. And we have evidence that this is a particularly effective, powerful strategy, as I say, from undergraduate computer science education, where the students who spend time reading other people's programs rather than immediately going on and writing their own program, forgive the expression, from scratch, actually do better in terminal exams than those who've just spent their time writing code. So we can do examples of this. Here's some logo code up on the screen here. If we had the microphones to bounce around, I'd say, what will this draw? But, talk to the person sat next to you. What will happen when I run this program? What sort of shape would appear on screen? You're allowed to use pencil and paper. Okay, is this what you expected? Anybody got it right? Okay. The being able to run that in your head is far, far more important in terms of thinking like a computer scientist than just being able to type those lines of code in and press the green flag to run the program. And other similar things here. So here's a little Scratch program. Click on the green flag, go to these positions, point in a direction, set the speed, and then follow this loop forever. If the yellow thing touches the green thing, turn one way. If the blue thing touches the green thing, turn the other way. What's going to happen when we run this code? It kind of depends on the state of the system. But if I show you the state there, this is what it's written for. We have here the algorithm for the self-driving car. And I'm fairly certain that somewhere in Google's self-driving cars, there's going to be a rule which says, if you go off the road to the left, turn to the right. If you go off the road to the right, turn to the left. There will be other rules as well. But being able to read the code is, we think, more important than just being able to write the code. One way to scaffold the writing of the code is to give children some pre-built bits of code and say, change it so that it does this, or add to it so that it does that. Start with a template, start with a writing frame, if you will, and see what you can do to change it. All of the examples on the screen here, Scratch, WordPress, Moodle, Android, Firefox, and the Linux operating system, are open source software. Anybody can come along and download the source code for these things from their website. You can read how these have been built. Okay, we're not doing this with our 5 to 7-year-olds, and then you can edit this. You can change how these things operate. Doing that to Linux or Android is kind of ambitious, but doing that to WordPress or Moodle is built with that sort of modular architecture in mind. And of course, Scratch does this as well. The most exciting thing about Scratch is not the lovely way that the blocks fit together to make a computer program, but the little share command up there at the top of the screen. So you can take your program, you can share what you've made with a global community of other Scratch programmers. You can also see what they've done, download it, or edit it online, tweak it, make it better. So I've written a commercial scheme of work for computing. We start with the duck shoot game. The duck flies across and you have to fire the arrow up to it. And there are 100+ remixes of that game that young people have taken my code and made it better, which is just so very, very inspiring. Some of those really quite weird on balance. And something like this, which is teaching a very subtle, complex, deep idea of computer science, the notion of recursion. Trying to sit a class of children of age 11 in front of you and explain the notion of recursion is hard. But tweaking a program which has recursion there and seeing how the changes you make affect what it produces, that's easy, and it's a good way into scaffolding these subtle, these complex ideas. So just changing lines of code in this software produces really quite different looking trees on screen. These are quite deep ideas. Writing a program to do that, hard. Editing a program that already does one of those, easy. And we get into conversations around how come the natural world looks so similar to this sort of fractal type design there? What's the notion of recursion when it comes to nature? Which makes things very interesting. Okay, so it's about the thinking, it's about, you don't have to use a computer, it's about reading code, it's about editing code, but sooner or later, and kind of bullet point 5, we have to admit that making your own program is the most fun that you can have with this. It really is. And we want children to have that experience of making something of their own. And again, we go back to Seymour Papet's idea that children's making mental models, the mental schema, how the world works. Yes, you can do that through play. Yes, you can do that through conversation. But actually, this seems to work particularly well when we make something. Making something in the world to make something in your head lies at the heart of Papet's notion of constructionism. And we want children to have that experience. Of course we do. How are we doing for time? I'm not going to show the video, but we get children making things with Lego. Go and have a look at the Lego education stand and writing the computer programs to do that. So they're making things in the world, they're making things on screen, which really helps them understand the ideas at the heart of computer science. It's lovely for me seeing what children do. So again, this commercial scheme of work, seeing how children have taken those lesson plans and then built their own drill and practice maths game to share with the world there. It really is lovely to see these things. Our friends at Ofsted, the English Education Inspectorate, say that achievement in computing is not satisfactory, is going to be inadequate if pupils rarely demonstrate creativity or originality in their use of computing, but seem confined to following instructions. There are a number of products in the English computing market space which have, on the left-hand side of the screen, a list of steps that you have to follow. On the right-hand side of the screen, the place where you write your program, where you build your code. I really do worry about this. It's better than nothing, but it isn't the same as giving children the opportunity to create something of themselves. Just following instructions is closer to programming children than teaching children how to program. Getting children to work collaboratively seems an important part of the process as well. The photograph here is one of Google's offices. Software such as Google and Microsoft and Apple and Facebook make is not written by lone people working in darkened rooms. It's written by teams of people bringing their own experiences, bringing their own understanding to the process. Now, we're discouraged from doing that when it comes to public exams back in England, but not in the primary phase. It's really very, very effective pedagogy for children to be working together. And this, as I say, is how big software gets written. We have strong, robust evidence that pair programming, very, very powerful development methodology, getting two coders to work together on one screen, one keyboard, one mouse. They produce better, more elegant, more reliable, less buggy code than two coders working separately and trying to join the projects together. This is a real-world software development methodology. We should be using it in education too. So with my own students at Roehampton, we set them the task of using Scratch to make an educational game. And they could all do this, of course they could. But they get so much more out of the process by working with a partner to do this. And of course, being able to work collaboratively in a team, kind of important in terms of 21st century, third millennium skills, as we know. It also seems a really effective pedagogic approach. There's work done in the States, again with undergraduates, about peer instruction. Putting the question up on the slide and getting students to talk to one another about their answer, and then vote as to which answer they, as a pair or as a team, agree on, far more effective than just assessing individuals' knowledge and then telling them where they went wrong. This learning from one another seems to matter a lot. Programming is hard. They will make mistakes when they code. Even if they've done the logical reasoning, even if they've done the planning thing about what will this do, it's still going to go wrong. We shouldn't worry about this. The slide here, of course, is Grace Hopper's notebook from the early days when computers were made of electromechanical relays. So the moth flew in between the blades of the relay, electromagnet couldn't close it, computer stopped working. What do you have to do? You take the tweezers and take the moth, or the bug as they call it in the States, out, and then the computer works. And Grace sticks into the notebook there, relay number 70, panel F, moth in relay, first actual case of bug being found. And maybe we ought to get children keeping a record of the bugs that they find and sticking them into a notebook, perhaps, perhaps not. My friend Quentin Cutts up at Glasgow University did the experiment with his undergraduates, this growth mindset idea. So 200 or so undergraduate computer science students, half of them he just taught the computer science stuff. The other half he taught them, yes, the computer science, but also about the importance of having a positive attitude towards learning from mistakes, or what to do when it gets hard, this growth mindset idea. And guess which half did better in the end of course exam? And of course, it's the growth mindset half. Seymour Papert had these insights back in 1980, that if children, young people, could take their attitude to debugging their programs and apply that to their first language learning, to their mathematics, to the other subjects they study in school, far more positive attitude to learning from our own mistakes across the curriculum would do an awful lot of good. And we can do examples of this. We can create examples in Scratch of what goes wrong with this program. And again, if we had more time and microphones, I'd do this as an exercise for you guys. This is meant to be a drill and practice maths game. You run the code and it keeps asking the same question over and over again. That's because the random variables are initialized outside the loop. Fixing this is a useful skill to have. This is one which not everybody in England agrees on. I'm very much of the view that there are certain fundamental ideas here and we need to focus on teaching those ideas. The national curriculum we have says, understand and apply the fundamental principles and concepts of computer science, have repeated practical experience in writing computer programs in order to solve problems. I don't think we need to teach loads and loads of different computer programming languages in order to do this. It seems to me, and at least some of us in England, better to focus on mastering one or two languages than to have just a superficial flavor of many. Certainly if this is a programming for all-like approach. We have this idea of the threshold concept, that once you see something, your view of the world changes, but it's hard to acquire that knowledge. I think you only see these ideas if you focus on mastering one or two or three programming languages rather than a flavor of many. How many programming languages do you need? Depends on the age of the child. 5 to 7-year-olds, the little robots plus Scratch Junior. 7 to 11-year-olds, Scratch as our focus, as the best language we've found for this. Maybe Kodu, because Kodu brings in this idea of event-driven programming. Maybe Snap, because Snap implements functions. 11 to 14-year-olds, Snap is fabulous, is scaffolding that transition from primary to secondary, and Python as our text-based programming language of choice. And then for 14 to 16-year-olds, Python seems to have captured the imagination of teachers in England. Up in sixth form, 16 to 18-year-olds, another language then, Java to focus on object orientation, or even, with one of our exam board, functional programming through a language such as Haskell. Snap, if you've not tried it, do. If you're familiar with Scratch, you'll be able to get started in Snap straight away. But Snap brings in the ability for a function to return a value, and that opens up no end of possibilities in terms of theoretical computer science as well as applications to mathematics. The example on screen there is about creating a demonstration of fractions arithmetic or a system for fractions arithmetic using Snap. The context of their coding does seem to matter as well. Our friends in the Education Inspectorate say you've got to have real-world, authentic context for children to learn these sorts of ideas, and that includes applying that across the curriculum. We have some lovely programming projects. So there's a program called Apps for Good, where children, typically 11 to 14, create the idea or think of the idea of a socially beneficial app for a mobile phone. Android, iPhone, doesn't really matter. They pitch the idea, they design the user interface, and then, and only then, do they worry about the coding thing. I love the Apps for Good stuff because it provides a context and it brings in the other bits of software engineering and computer science that the programming alone doesn't touch. We had Young Rewired State and some brilliant solutions there. So my favorite of those is the Pumps app, which does the automatic number plate recognition at the petrol station, and if you try and put petrol in the diesel engine car, shuts off the pump. Clever idea, would have saved me £100 on one occasion. We have wonderful platforms for physical computing, such as the Raspberry Pi, brilliant for 16 to 18-year-olds to work on. It's pre-university projects. And of course, the microbit, which some of you heard about earlier, over on the British Pavilion over there, if you want to see one of these in action. My final point, you'll be relieved to know, is what we've done with the English computing curriculum is make it an entitlement for every child in the country. This is the really radical thing, not teaching computer science to primary school children, but teaching computer science to all primary school children. That it doesn't matter if you're a girl or a boy. It doesn't matter if you came from a wealthy home or a socially disadvantaged home. It doesn't matter if you have particular special educational needs. You still have an entitlement to be taught computer science. So we're doing things to address the gender imbalance there. Not this sort of thing. This is computer engineer Barbie. Your robot puppy is so sweet, says Skipper. Can I play your game? I'm only creating the design ideas, Barbie says. I need Stephen and Brian's help to turn it into a real game. We're wanting to move beyond that notion to this is something everyone can do. As I say, irrespective of social background, irrespective of special educational needs, irrespective of first language. Scratch, again, very, very good support for additional languages. Here's my list of 10 things all over again. I'd love to know what you think I should have mentioned, or if there's anything on this list of 10 that you would strongly disagree with yourselves. Just 3 closing remarks. The academic, University of Roehampton, says more research is needed. Not an entirely disinterested observer here. The meta questions. Can we take the findings from effective teaching in general and apply those to this particular domain of computer science education? Can we look at the research that's done with undergraduate computer scientists and apply that to 5-year-olds learning to program? They're both novice programmers, but 5-year-olds and 18-year-olds seem different to many of us. My friend Sue Sentence has a number of classroom research projects which CAS teachers, computing at school teachers, are engaged in, and we as an organization have a number of research questions that we would very much like the answer to. Top of the list there, I've attempted to give some thoughts on today. How should we teach programming to children? We're kind of figuring this out for ourselves, and that's what makes this so exciting for us as teacher educators and for the teachers that we work with, of inventing our own pedagogy for this. All of these slides are online, bit.ly NTE17B, and my contact details are up on the slide. I'll hang around at the back to chat. Thank you so much for your patience this morning. Thank you.